All right, welcome to The Explainer. Today, we're going to pull back the curtain on something you use every single second, but probably don't think much about the internet's core infrastructure. We're going to get into the nitty gritty of how every single piece of data, your emails, your videos, everything, gets from point A to point B. And if you're studying computer networks, you really need to know this stuff. So, here's our game plan. We'll kick things off with the core highway of the internet. Then we'll get into the big debate, packet switching versus circuit switching. We'll look at the trade-offs and then see how this one decision basically built the internet we use today. Okay, let's just dive right in. I mean, have you ever really stopped to think about how an email you send from, say, London can hit a server in Tokyo in the blink of an eye? It's kind of magic, right? Well, that whole journey kicks off in what we call the network core. Think of it like a massive, super complex highway system, but for your data. So what is this network core really? At its heart, it's this giant tangled web, a mesh of interconnected routers and the links, the cables and fibers that connect them. This is the backbone of the internet. It connects all of us, our devices, which are out on the edge of the network. But here's where it gets interesting. When it comes to actually moving data through this core, there are two totally different ways to do it, two competing philosophies. And this right here, this is the fundamental choice, the big fork in the road for network design. You've got packet switching on one side. That's the internet's way. It's all about being flexible, sharing resources as needed, on demand. Then on the other side, you've got circuit switching. This is the old school, traditional way, where you actually reserve a dedicated private lane just for your data. All right, so let's dig into the one that actually won, the approach that powers literally the entire modern internet, packet switching. Here's the core idea. When you go to send a big file, like a movie or something, it doesn't just go out as one massive single block. No way. The network is way smarter than that. It chops it up into thousands of little, manageable pieces we call packets. Okay, now listen up, because this next concept is absolutely crucial. If you're studying for an exam, this is the part you want to highlight. It's called store and forward transmission. It sounds technical, but trust me, the idea itself is actually pretty straightforward. So this is how it works. A router isn't like a simple pipe where data just flows through. No, it's more like a post office sorting room for each individual packet. It has to receive the entire packet, every single bit of it, and store it in its memory. We call that a buffer. That's the store part. Only then can it look at the address, figure out where it needs to go next, and start sending it out. That's the forward part. And this happens over and over again at every single router on the journey. So as you can probably guess, this whole store and forward thing at every stop adds up. It introduces a delay. Now, for all you students out there getting ready for an exam, this is where the math comes in. The time it takes to push one packet across one link is its length, let's call it L, divided by the link speed or rate, R. So L over R. And since this has to happen for, say, n links along the path, the total delay is roughly n times L over R. It's a simple approximation, but it tells you something really important. More hops or bigger packets means more delay. Simple as that. Okay, so what happens when a whole bunch of packets show up at a router at the same time, faster than the router can send them out? Well, it's exactly like a traffic jam. Picture cars hitting a toll booth during rush hour. What do? They have to get in line, they have to queue up and just wait their turn. In the networking world, we call that waiting line an output buffer, or just a queue. And these queues, they're the reason your internet connection sometimes feels unpredictable. It's why you get variable delays. But here's the real kicker. These queues, these buffers, they're not infinitely long. They have a finite amount of space. So if a new package shows up and the line is already full, tough luck. The router has no choice but to just drop it. It just gets discarded. And that, my friends, is what we call packet loss. Okay, so that's packet switching. Now let's switch gears, no pun intended, and look at the alternative. This one comes straight from the old school telephone system. It's called circuit switching. The absolute best analogy for circuit switching is making a reservation at a fancy restaurant. You call them up, you tell them you need a table for 2 at 8 p.m., they reserve it for you. When you show up at 8, you don't have to wait in line with everyone else. Your table is there, guaranteed, ready for you. It's yours. And that is precisely how circuit switching works. Before you send even a single bit of data, the network establishes a dedicated end-to-end path for you. We call that a circuit. It carves out and reserves a guaranteed slice of the bandwidth on every single link along that path, and it's reserved exclusively for you for the entire session.
So you're probably thinking, wait a minute, how can one physical cable, one fiber optic line, support hundreds of these private, dedicated circuits all at the same time? Well, the magic trick that makes this possible is a technique called multiplexing.
And there are basically two classic ways to pull this off. First, you have frequency division multiplexing, or FDM. With this one, you take the entire frequency spectrum of the link and slice it up into different bands. It's just like radio stations. Each station gets its own frequency, and each of our circuits gets its own private frequency band. The other way is time division multiplexing, TDM. Here, instead of slicing up the frequency, we slice up time. Time is broken into frames, and each frame has slots. Your circuit gets one time slot in every frame. It's like a perfectly organized round-robin conversation where everyone gets a turn to speak. And all of this brings us right to the heart of the matter, the great trade-off between these two methods. And this, right here, is the fundamental reason the internet was built the way it was. Okay, so here's the bottom line. Circuit switching is amazing for guarantees. You get a constant, predictable performance, no question. But it's also incredibly wasteful. Think about that restaurant reservation. If you book the table and don't show up, that table sits empty. It's the same here. If you reserve a circuit and don't send any data, that slice of the network just sits there, idle. Now, packet switching, it offers zero guarantees. Your data might get delayed, it might even get dropped, but, and this is a huge but, it is ridiculously efficient because resources are only ever used when there's actually data to send. And trust me, this efficiency thing isn't just theoretical, it has huge real-world consequences. Just look at this scenario. Let's say you have a 1 megabit per second link. With circuit switching, you can only support 10 users who each need 100 kilobits per second. That's it, you're full. But with packet switching, because our internet use is bursty, we click a link, get data, then we sit there reading, it can support more than 3 times as many users on the exact same physical link. It's just a way more economical way to build a massive network. So for our final piece, let's zoom all the way out. How did this one choice, going with packet switching, allow the internet to explode from a little research project into the global network of networks that we all depend on every day? You see, the internet isn't one big company. It's not a single thing. It's actually a massive collection of thousands of separate networks all hooked together in a kind of hierarchy. It starts with you, your home network connects to a local internet service provider, or ISP. That ISP then connects to a bigger regional ISP, and those guys connect to a small number of absolutely massive globe-spanning Tier 1 providers that are the real backbone of the internet. This whole decentralized structure only works because of the flexibility of packet switching. You don't need to create one single dedicated circuit across all these different companies' networks, which would be a nightmare. And what's the glue that holds all these thousands of networks together? Well, a big part of it is something called Internet Exchange Points, or IXPs. These are just huge physical data centers where all these different ISPs can plug into each other and exchange traffic directly. And on top of that, you have the giants, companies like Google or Netflix. They've built their own private global networks just to get their content from their data centers to your ISP as fast as humanly possible. And all of this leaves us with one final really interesting question to chew on. Packet switching was without a doubt the perfect choice for the early internet, which was all about text and file transfers. But think about today. We demand flawless live streaming, online games where every millisecond counts, and immersive VR. So will the very thing that made packet switching so great, its lack of guarantees, end up being its biggest weakness in this new real-time world? Well, that's a problem for the next generation of network engineers, maybe even you, to figure out.